Hello again. In this lecture, we're going to continue our discussion of phase equilibrium and the relationship to phase diagram. So the whole idea is that we wanted to know if we have the Gibbs energy as a function of concentration, how can we interpret and relate that to the phase diagrams. And this will be pretty much the last lecture in the series about phase diagrams and the construction of phase diagrams. So I'm going to start from where we ended up on the previous lecture, and that will be summarized here. So if you look on this lecture here, if you look at what we have basically the Gibbs energy as a function of concentration for phase alpha and also for phase beta. The green line is for phase beta, and then we use the equilibrium, which is summarized here, that the chemical potential of element A, this is element A, in phase alpha must be equal to the chemical potential of the same element in phase beta, and that is evaluated at the concentration of element B in phase alpha, and this one here is evaluated at the concentration of element B in phase beta. This is the green line, so this is the green point where it is calculated, and this is the red line, and here's the red point where it's calculated. The mu is not the slope of the curve, but it is the intercept. So the mu for the red line is the red arrow here that represents intercept on the A side, and that is the value of the chemical potential. On the green side, which is phase beta, then the mu is again the intercept, and it's the green arrow. And as we notice here is that if we have the common tangent, the intercept of the red line is the same height as the intercept of the green line, and that solves this equation that you see here, and this equation in A. We can write another equation in B in the following sense. So we can write another equation that tells us mu of element B in phase alpha evaluated at x sub B in phase alpha is equal to mu of phase of element B in phase beta evaluated at x sub B in phase beta. So now what we're looking for is this number and this number. These are two unknowns, xb in alpha and xb in beta. So we have two equations, equation 1 and equation 2, and we solve them simultaneously, and the simultaneous solution of these two equations will essentially give us the values of the concentrations that will give us equilibrium. The concentrations turn out to be, we have two values for the concentration of B, one related to the phase alpha, one related to the phase beta. We can also obtain the same result numerically, because in a lot of cases we have equations. So in order for us to solve the same problem numerically, as we have noted, then the G function is nonlinear in the concentration. It has quadratic terms, and it has also logarithmic terms, and therefore the solutions cannot be obtained by simple substitution. And the solution, if we have a MATLAB program, we can solve two nonlinear equations and two unknowns using Newton's method, for example. There are functions in MATLAB that can do that. If we want to program ourselves, then here is the way to program and get the solution. Here, the x is a vector, and the x vector is tell us the concentration of B in phase alpha and the concentration of B in phase beta. These are the two unknowns that we wanted to actually solve for. So we wanted to solve for these two unknowns if you look at it from the previous page. Then suppose that we make iterations. So iteration m equals 1. We assume xb of phase alpha to have a certain value, and xb in phase beta has also an initial value. So this is initial guess that we would have. And then we would go to, now if the initial guess, if we guess is right, then this vector m, which is the difference in the chemical potentials of element B in the two phases, that difference should be 0 when we have equilibrium. But if it is different from 0, then we can use it so that we can find a better estimate. And the better estimate is obtained by using an iterative Newton method like this, where we have xm plus 1 is equal to xm minus the inverse of the Jacobian matrix times this vector m. Vector m is the residual vector that gives us, if it is 0 or close to 0, then we're done. If it is not, then we have to keep the iteration. So the Jacobian is the derivative of mu with respect to x sub b and mu with respect to x sub a in the two phases. So it means that not only that we have to find g as a function of x, but we have to also find the derivative of g and then substitute it and get the mu, and then input that into the j, which represents the Jacobian, and have another iteration m sub 2. It gives us xb and alpha, and this is, we can evaluate it from iteration number 1, and xb in beta, and that we can evaluate from iteration number 1, and continue this until we have convergence of the solution. So that's pretty much a numerical method, and the numerical method that you see here so the numerical method that you see here is very general because and it's important because if we have say many phases and many species, we now have to make a system of equations with an initial guess and the vector of the concentrations of B, let's say, in a three-phase system, like if we have liquid and phase alpha and phase beta, these are three phases, then the vector is going to expand because we want to have x sub b in the liquid, x sub b in alpha, x sub b in beta. This system that we will discuss in a minute will produce something called eutectic, which is very important. But nevertheless, you will have three equations, and the three equations will have to iterate until you get the solution, appropriate solution. If the guess is correct, then the convergence will be very fast. If it is incorrect, then we may have to kind of iterate more until we reach a final result. So in the following, what I will do is I'm going to describe now two situations for phase diagrams. One in which we have a liquid, and the liquid is in equilibrium with one single phase. For example, if I have copper, and the copper has a liquid phase and a solid phase. Or if I have a copper nickel alloy, and the copper nickel alloy can have a solid phase and a liquid phase. And there's only one solid phase. So I have one solid phase and one liquid phase. Then in this case, what happens if I increase or decrease the temperature? We'll find out, as you will see, that we have something unique here. There will be a unique concentration in which the entire alloy will melt from the solid phase into the liquid phase. So there's a unique concentration. And this unique concentration gives the terminology, as we know, it's called congruent melting. So the melting will be congruent, and exactly at that kind of concentration. So this is one case. And then the last case that we will study for phase diagrams is the case of the eutectic. And the eutectic is a composition, very unique composition also, of an alloy. Suppose that I have a copper silver alloy, then it'd be a specific composition at which the alloy will have the lowest melting point. So the alloy at that composition will have the lowest melting point, and therefore I can actually utilize this composition to melt it very quickly, and then I can add some other things to get it away from that composition if needed. So the idea of eutectic is an important idea. And the eutectic, I don't have two phases, I have three phases. Again, I have two elements, A and B, but I have three phases, and I would like to look at the equilibrium. And we'll finish the discussion with an example on how to solve for the eutectic phase diagram with an example and some unique aspects in the phase diagram, as we'll see. So let's first look at the congruent melting. And then here I have this two-phase equilibrium, congruent melting, and this two-phase equilibrium shows me that I have on this side here, I got, let me just pull myself here, I have the liquid phase has at the high temperature, for example, then I have a liquid phase that has a Gibbs free energy lower than the alpha phase. So this is lower than the alpha phase, and therefore at this high temperature, where the temperature is greater than the congruent temperature, the liquid phase will be stable, always stable. And for any composition here, the alloy will have a liquid phase. Now, if I decrease the temperature until I hit this specific and critical temperature T congruent, then what's going to happen is that the solid phase alpha is going to be tangent to the liquid phase G liquid, and they both have a common tangent that has the mu alpha on the mu of element B on one side and the mu of element A on another side, where the mu's of the liquid and the alpha phases are equal for the two elements. That's the solution. But because they are touching exactly at one point, that will be a unique point, kind of a singular solution. If we have this concentration X congruent, then if I increase, if I'm at this concentration and I decrease the temperature up to the congruent melting point, then it will immediately solidify into a solid phase below that temperature. So this is very critical if we do solidification, for example, and casting. On the other hand, if the temperature goes below the congruent melting point, then the alpha phase, which is a solid, can have Gibbs energy lower than the liquid phase in a limited range, and therefore it should be more stable. So the stability is again determined by the common tangent on the left side and the common tangent on the right side. So I will have here to look at the common tangent here that gives me two solutions. So let me expand this a little bit more. So I have here on this tangent, I will have a region, and this region will have liquid on this with this composition, and solid with this composition. So this is a two-phase region in here, liquid and solid. On the other side, I have also a two-phase region in here. But look at the middle, in the middle between the two regimes, I will have essentially a solid, and the solid, which is a single phase, the alpha phase. And in this case, it depends on the composition. If the composition falls between the XB alpha on the left and XB alpha on the right, then I have a single alpha phase. If it falls in the other two regimes, then I will have a mixture between liquid and the alpha phase. So this is the idea of congruent melting that we describe here. The next idea that we wanted to discuss is the fact that we'd be interested in having equilibrium between three different phases. Suppose that I have an alloy of copper and gold, and the alloy is melting, and the alloy, of course, when it's high temperature, it will be at a single phase, liquid, but at lower temperatures, it may have a regime that has more gold into the copper, and a regime that has more copper into the gold, and corresponding structures, we can call them an alpha phase, and then another structure we can call it a beta phase. So alpha and beta are two different spatial structures of the copper gold alloy. So we need to study the equilibrium of this alloy. So in here we're dealing with three Gibbs free energy functions as a function of the concentration of one of them, which is x sub b as usual. So I have here, if I expand this, so if you look on this side, I have now the, you can see it, I have, this is the molar concentration of the alpha phase, and this is the liquid, and this is the beta phase. As you can see, that I have at a temperature greater than what we call the eutectic temperature. If it is greater than the eutectic temperature, then I have the liquid is very stable, and is stable between these two regimes. So between here and here, then I have a liquid region that is very stable. And on the between, let's say if I can change the color, in this region here, I have a two-phase separation. One would be liquid, and the other one is going to be the beta phase. And on this side here, I have separation into a liquid phase and an alpha phase. If the temperature now is adjusted so that it's lowered to a point where we have the following situation here, and in here I have the case that I succeeded in finding a temperature in which I have a common tangent to the three functions, the Gibbs free energy of the liquid, the Gibbs free energy of the alpha phase, and the Gibbs free energy of the beta phase. Then I must have a situation in which the three phases are coexisting together. This is called the eutectic situation, and this is the lowest possible melting point that we will see on the phase diagram. So in this eutectic condition, I have three coexistent phases, and I have on each phase the concentration of element B is given here. This is in the alpha phase, this will be in the liquid phase, this is in the beta phase. So I have three different concentrations, each one is consistent with its corresponding phase. If you now lower the temperature a little bit more, then you get into a situation that the whole alloy is solid, and the liquid phase Gibbs free energy is too high, so it's not stable. The stable is going to be both the liquid and I mean the solid alpha phase and the solid beta phase, and the stability condition is expressed by the two of them being lower than the liquid, and then the equilibrium condition is expressed by the common tangent of the two, giving you these two solutions. So I have a solution here and a solution here for the two concentrations corresponding to the two phases. So if I want to translate this to a phase diagram, how does it look like in the phase diagram? This is basically a free energy diagram versus concentration. A phase diagram will be the temperature versus the concentration. So how does it look like? It will look like this. So let me just kind of show you now how the situation is going to work out. So if I am at high temperature, at temperature T1, this temperature is all liquid, obviously, in here, because the liquid Gibbs free energy is the lowest. And then it depends on where I am in the concentration system. So if I am on this side, suppose in this side, and I'm cooling down, so as I cool down, as I enter into this phase boundary to T2, let's say in here, I'm at this temperature T2 and at this concentration, then I will have a separation of phases. I'll have phase that is gamma, or liquid. Gamma is the liquid. And another phase here that is alpha. So I have a concentration here corresponding to alpha. And these are the two corresponding concentrations from the phase boundary. And I can do that on the other side, of course. If I have a concentration coming down here, it will split into the corresponding points in here that, in fact, we're going to tell you how to determine them with what is known as a, as a lever rule that we'll learn about in a few minutes. So let's say for some reason I have now a situation where I have the alloy is actually has a composition that just goes right into here. So the initial point is right here and the final point is right there, and I'm decreasing the temperature. So as you can see, the decreasing in temperature, when I hit this particular value of the temperature, T eutectic, I'll have three phases. One phase will be the beta phase right here with the concentration of X sub B. One phase will be the liquid phase with the or gamma phase, and then one phase will be the alpha phase with the concentration given by this point in here. So these are the three that will come out. And this point is called an invariant point in the system, or the eutectic point in the system. So we're going to be able to solve problems now in which we have two elements, copper and gold, and we'll approximate their phase diagram with, instead of these curved boundaries, we'll approximate them with straight lines, and then we'll see how we're going to formulate a solution of a problem for the copper and gold, as you can see in the homework assignment. So let's look at this particular example in here. So in this example that we have here on the board, we have an alloy, and the alloy is shown in here, and the alloy has a silver copper, and it goes from the liquid to the alpha and beta phase. And the alloy's composition is 65% copper, so it means that I'm right here. 65% would be, let's say, about here. 65% copper. If this is the copper composition, so it would be on this side. And it's cooled from 1100 degrees C, so it is from this point, and then it's cooled down. And we want to calculate the fraction of the alloy by weight, which exists as beta phase at 850. So at 850, I want to compute what's happening here, and compute just above the eutectic and below the eutectic and so on. So you have various things that we need to compute here, and we wanted to be able to determine the fractional concentrations. Now the phase diagram, in this case, the solutions, we can obtain the concentrations for the equilibrium directly from the phase diagram, since the phase diagram really represents the boundaries that we found from the solutions obtained from the Gibbs free energy. So the phase diagrams will be very useful by themselves just to determine these concentrations immediately. And what I wanted to show you now is kind of an interesting method to determine the equilibrium concentration. Is called the phase rule, as we'll see it here. So if we look at the phase rule here, before we get the liver rule that I wanted to discuss, and the liver rule is something like this. So let's say that I have the concentration, like a section of the phase diagram, and this section is illustrated here, and I have the two lines here. Let's say one line here and then one line over there, and then at some temperature I have now a section, I have a temperature like this, and then I have an alpha phase here and a beta phase, and I have an alpha plus beta in the middle. And moreover, I get now a concentration, and I'm decreasing the temperature until, this is the temperature, until I hit the particular value that I'm interested in, T2 for example, and the initial concentration is x0. Now I'm talking, what is x0? Is basically xb, a specific value of xb. So let's assume that the value here is denoted by x beta, and the value here is denoted by x sub alpha. And then we're going to write this as called the tie line. So the tie line that represents the constant temperature, or isotherm, if you will. And then what we want to do is find these solutions, x beta and x alpha, in a very simple way. So instead of having all of these calculations using Gibbs free energy, we're going to just use some simple rules that will develop in here. So in order for me to do that, let's just say that we have to write conservation equations. So the conservation is going to be, if I have one conservation equation for the number of moles, if the total number of moles is split between the alpha phase and the beta phase. So these are the moles in the alpha and the beta phase. The second conservation equation is a conservation of species. So the species conservation, initially I have x0 times n. This is the amount in the amount of B in the initial alloy, and now B split between the alpha and the beta phase. It's split such that I have x alpha in the alpha phase and x beta in the beta phase. Now these are the solution of these two equations should give us the unknowns. So these are two equations in two unknowns, and the two unknowns that we are looking for are x alpha and x beta. And we know, or n alpha and n beta, for example, if we know x alpha and x beta, then we want to find the corresponding, say we can, if x alpha and x beta are known, let's say from the concentrations we know that, and x0 also is known, then what we want to know now is what is the fraction that is in the alpha phase. This is a fraction of moles, And what is the fraction of moles that is in the beta phase? I'm going to call it W of beta. So these are things that we can find. What is really interesting about these equations is that you can see that the first line is like force equilibrium. So it's the total force is split into two forces. And the second line looks like moment equilibrium. So the total force times a distance is equal to the force alpha times its distance plus the force beta times its distance. So from this type of analogy with mechanics, I can just maybe make a very simple characterization of these two equations. Let's say by going back here and assuming that I have a reaction force here. So I'm going to assume here that I have a reaction force, and this reaction force is capital N. And then on these two sides, I have two forces. One is N beta and one is N alpha. And moreover, in between them, this looks like a teeter-totter or a lever. So that's why it's called the lever rule. And the N is balancing, this N is balancing N alpha and N beta. So the balance N equals N alpha plus N beta is actually the first equation here. And then if you think about it, now if this is 0, if you take the 0 is right here, then the N multiplied by this distance is x0, is equal to N alpha multiplied by this distance, which is x alpha, plus N beta multiplied by this distance, which is x beta. And that's exactly the second equation here. So I can use this idea of the lever rule to immediately derive the fractions of alpha phase and a beta phase in a very simple way. So let's do that by looking at it this way. So if I look at a situation that has a lever here, and I have now, this is, say, situated here, this is your N, and then I have these two forces, one here and one there. So this is your N, and this is your N alpha, and this is N beta. And this distance is x0. This x sub alpha, sorry, x sub, maybe I should just make it consistent with the previous to have the alpha here and the beta there. So I have N alpha, and this is x alpha, and beta, and the distance is x beta, and N has the distance x0. Then we'll say we can, instead of taking the moments about some point in here, we can take the moment about this point in here of the application of the force N, and that the reason is that that can eliminate the product of N times its arm. So it means that N alpha times this distance, which is x0 minus x alpha, must be equal to N beta times this distance here, which is x beta minus x0. And then we know that N is equal to N alpha plus N beta, and from these two we're able to find the alloy, the fractional concentration of the two phases. So we can now write N alpha over N is equal to x beta minus x0 divided by x beta minus x alpha. And N beta over N is equal to x alpha minus x0 divided by x beta minus x alpha. And these are the fractional concentrations W alpha and W beta that we are looking for. So that's basically a simple way that we can use to solve for the fractional concentrations of the alloys, W alpha and W beta, like these two. And given that we know the boundaries, and in the previous problem that I showed you, we're going to assume that the boundaries are just basically straight lines. And if from the straight line equations, you can find these concentrations x beta, x 0, x and x alpha very easily, and therefore you can find the fractions of the liquid and alpha and the beta the liquid and the alpha and the beta phase. Okay, there's only one thing left now, and this is the fact that in phase diagrams we don't use molar fractions, unfortunately. The reason is that we use just weight fractions, and we need to know how to convert from a molar fraction to a weight fraction and vice versa. And that's what I'm going to do next, is that the conversion between molar and weight fractions. And we'll do that in the next example, in which we want to talk about molar and weight fractions. So if we want to have, let's say we have a molar fraction that we want to find, and we know the weight fraction. So we know Z is a weight fraction. And we want X, which is a molar fraction. So we want to go this way from a Z to X. So let's say we have an alloy that has A and B. So X sub A would be the number of moles of A divided by the sum. And the number of moles of A, if we assume that we have a mass, total mass, is equal to M, so I have a mass M, then I'm able to write Na will be the mass of A, which is its weight fraction, or mass weight fraction A, ZA times M, divided by the mass of A. And this is Ma is the molar mass. This is the molar mass. And then the same thing here would be ZA times M over the molar mass plus ZB times M over the molar mass of element B. If I multiply up and down, then I find that X sub A is equal to Z sub A times the molar mass of B divided by Z sub A times the molar mass of B plus 1 minus Z sub A times the molar mass of A. And therefore now I have a way to convert the masses or the fractions from weight fractions to the corresponding molar fractions that we use in all of our thermodynamic calculations. And this will give us the ability to now use or just go between the phase diagram and the Gibbs free energy diagrams. The Gibbs free energy diagrams are based on molar fractions, while the phase diagram is based on weight fractions. So in order for us to do that conversion, if the weight difference is very large, then you can have a huge difference. If the molar masses are similar, then the changes are not going to be that large. But anyway, we have to do that conversion whenever we go from the solutions and the molar solutions that we get from thermodynamics to the liver rule solutions that we actually get from the phase diagrams. So when I talked about the phase diagrams in the last few minutes, I started talking about the phase rule, and I used the script X. That should be replaced by Z, because Z is actually what is given to us in phase diagrams, and then we have to go back to X if we need to convert it for the Gibbs free energy. And with that, I think we have a pretty good idea about phase diagrams, and that will finish the series of lectures on phase diagrams, and we'll see you in the next series of lectures.